Online lecture number 12. Let's get started, but first look back. We figured out that the rate of a reaction is given by this expression. It's a differential equation where we have the concentrations of A and concentration of B with the order parameters and the the rate constant. And the question that we asked last time, what does this rate constant depend on? And we found it depends on the speed, the orientation, the size of the molecules, and also the energy barrier that the molecules have to overcome in order to undergo the reaction. And these concentration terms, they express basically the collision probability, right? So the energy barrier, again, is the activation energy that you have to reach in order to go to the transition state of the molecule. That then finally leads to the product at the lower energy. So, and the relationship between the rate constant K and the activation energy and these other three parameters is given by the Arrhenius equation. So when we spoke about reactions in the last two lessons, we totally ignored that there must actually be an equilibrium. We only spoke about going from A to B, but not this intermediate equilibrium state. So we always drew only one arrow, but in fact we have to draw two arrows, right? So there's an equilibrium between the reactants and the products, as we figured out before. So this equilibrium is now depending on the standard Gibbs free energy of reaction, as we found before, and the temperature. And for instance here it's about 80% of the product P in the final composition. And so what we can now do is we can assign a rate constant for the forward reaction. F stands for forward, and this basically tells us how fast do the reactants go to products. But at the same time we can also have a reverse reaction where the products react back to products, Kr. And these two now are in equilibrium. So when the system has reached its equilibrium, then there's a continuous reaction of A and B to products and products to A and B. And both rates are basically the same, right? It's not static. It's not that there's a fixed concentration of products and reactants, but there's a continuous transition from reactants to products and products to reactants. Just the rates are just the same at equilibrium. So you can now express the rate of the forward reaction with a rate law, right? So the concentration of A times the concentration of B times the rate constant for the forward reaction, right? So in the same thing we can do for the reverse reaction. So concentration of product P and concentration of product Q times the rate constant for the reverse reaction, right? So what I said before was at equilibrium, the forward rate and the reverse rate, they are equal, right? There's as much product generated as there is reactant back generated. And so for these two rate laws, you can just equate them because these two rates must be identical because that's our equilibrium here, right? So that's called dynamic equilibrium, where forward reaction and reverse reaction are the same, right? So we can rearrange now to obtain this ratio of the rate constants for the forward reaction and the reverse reaction. And then the right-hand equation looks like this. Does that look familiar to you? It's the concentrations of the products divided by the concentrations of the reactants, right? Yes, it's the equilibrium constant, basically. Oh, that's a surprise. So the ratio of the forward rate constant divided by the reverse rate constant is actually the equilibrium constant. Of course, I express it here in concentrations and not activities, but you could write these rate laws also with activities. What you get is the equilibrium constant. Wow, that's pretty cool. Okay, so let's analyze this a little bit. So say we have an exothermic reaction, right? So that means we have to overcome this activation barrier for the forward reaction, right? So that means for the forward reaction we can set up an Arrhenius equation to calculate the forward rate constant. So here the activation energy of the forward reaction is now in the exponent here. And so if the products now go back to the reactants in this dynamic equilibrium, we have also an activation energy for them. This is now a little higher in this exothermic case. So it's the activation energy of the reverse reaction. And again, we can simply write a Arrhenius equation with the activation energy of the reverse reaction. Okay, so we said before, the equilibrium constant is the ratio of the two rate constants. So here I form this ratio, and now mathematically I simplify it a little bit. Here we get the ratio of these two A values. And the exponent is now just the top exponent minus the exponent in the denominator. And now I define this the difference between the two activation energies, the forward activation energy minus the reverse activation energy. That's delta E. And now look, the delta E is basically the change of the energy going from reactant to product. So this is almost like the enthalpy of the reaction, like the heat that is released in the exothermic case to the environment, delta E. It's not exactly this, but it's close to it. So the equilibrium constant can be written like this then. It's sort of like an Arrhenius law, but now here's not an activation energy, but it's the delta E term going from reactant to product energy level. Oh. So now we spoke already about an exothermic reaction where we have to overcome this energy barrier. And now if we have an exothermic reaction, right, then the activation energy of the forward reaction is smaller than the activation energy of the reverse reaction. That means this minus that is smaller than 0. So it's negative. Delta E is negative here, right? So exothermic heat is released to the environment, right? So now what happens if we increase the temperature, right? Looking at this equation that we derived by combining the Arrhenius equation for the forward and the reverse reaction. So increasing the temperature in the denominator for an exothermic reaction, right? Delta E is now negative. So the negative and the negative become positive. So this whole exponent is now positive. And if I increase the temperature, what happens to the positive exponent? It becomes smaller. Yes, of course, it becomes smaller. The smaller the exponent, the smaller the exponential term here, right? So the smaller the exponential term, the smaller the equilibrium constant. So increasing the temperature for an exothermic reaction decreases the equilibrium constant. Sounds familiar, no? Here, an endothermic reaction. So now the activation energy for the reactants is higher than the activation energy for the products to go back to the reactants. All right? That means delta E is now positive, right? This is bigger than this. So we have a positive delta E. The negative makes it negative. So a negative number. Now we increase the temperature. Right here I write it. Endothermic delta E is positive. Increasing the temperature. What does that do? Since it's negative, the whole expression with an increasing temperature, I make it less negative, right? The less negative it is, the bigger this exponential term is. So the bigger the exponential term is, the bigger the equilibrium constant is. So increasing the temperature for an endothermic reaction increases the equilibrium constant, and we go more to products. Doesn't it all sound pretty familiar? We've derived the same conclusion before based on this equation. And this equation was, remember, it was obtained from the second law of thermodynamics combined with the definition of the equilibrium with the Gibbs free energy of the reaction. So we come to the same conclusion by two different approaches, two different descriptions, once with the Arrhenius law and once with the second law of thermodynamics. So you see how everything is closely linked in this discipline of chemistry, physical chemistry basically. So I think that's really fascinating. So here you see now like how the Arrhenius equation and the rate laws can give you deeper insights also into the equilibrium of a chemical reaction. Okay, next time.